there's the recording. I'll get PowerPoint up and from the current slide. So this will be beginning this time. But let's do a little bit of review then. Are you familiar with Blackboard? Yes. Okay, you use Blackboard before. So when you go to this course in Blackboard, the home page for this course, there's going to be a series of blue tabs here. And they go on and on. They scroll down at least once or twice. Okay? All the ones you really need are shown on the first screen. And they're grouped sort of, those blue tabs, about 7 or 8 each, or 9 or something like that, in 2 groupings, and there's more groupings underneath. And the first group, like the second or third one, it says something like syllabus and book information, or something like that. If you click on that, you'll find the syllabus for the course. And that will be in static form. You can just read it, whatever. Okay. Now, the one right below that says instructor information, or something like that. Is it Ashley?
Yes.
Okay. All right. Okay, nobody else knew it was coming since I called you up. Okay, under the instructor information, I don't have it there yet, but I'm going to put my locator card. The trouble is, I'm now this deep in trying to wrap up evaluations I'm the math department chair, so for all my full-time and adjunct instructors, and I'm making great progress, but I haven't gotten there yet, so I've got to get that finished, and then I'll do it and try to get little things like the locator card back in here. Okay, but that will go there. It's not there yet. Then go down to the second grouping, and somewhere about the 3rd or 4th place there, somewhere down there, it'll be one that says handouts, PPTs, that's PowerPoints, and more, or something like that. Okay? If you click on that one, you'll see a whole bunch of stuff. The first stuff you'll see is the research paper general instructions. And yes, we have a research paper due in this class. So if you'll read that, that's there in static form. Then there will be, if my memory's right, I think all the PowerPoints we can possibly hit for this course this term. Okay? That's chapters 1, 2, 3, 4, and 5. Now, we're not going to have all those, but we're going to hit as many as we can. But I'll put them all out there just in case. Okay? And they're in static form. And then some of the order on this may be wrong. There are some videos out there that either I found or students have found and said they found useful for the course. Websites, things like this, YouTube, whatever. So I put those there, and they'll have strange names like Prof. Rob Bob, or Slater, or Education Portal, something like that. Those are there if you find them useful, need them, they're there. But then, somewhere down in that mix, you'll see Math 125 YouTube videos. If you click on that one, you're going to see a whole string of videos, more than I've done in this class for sure. Okay? The ones at the top are from past classes that I've taught. Most of them from last spring. Okay? There may be a few not from spring, but earlier, but most of them last spring. But if you go down to the bottom of that, scroll down to the bottom, when you see syllabus show up, that's where we started this time. Okay? And if you click on that, then you not only read the syllabus, you hear me talk about it, emphasize, that kind of stuff. So I talk about the syllabus, I talk about the research paper instructions that you saw up here, but that was static form, you hear me talk about it. Okay? Yay, what a joy. Okay, you'll also see me talk about, or hear me talk about the locator card, which you don't have up there yet, but it will be at some point. And then we talk about things like safety, fire, weather, and active shooter, those kinds of things. We talk about safety issues. And then we get started in chapter 1.1. And right now we're in 1.3. So over the next few videos there, you'll see all the things that we've done in class since then. Now, I'll also say this about the book. Now, again, I think I've said this. A few of you are Lawson students. I know that. but I think more of you are transient students, right? Okay. If you have a calculus, well, you haven't started your calculus sequence yet. If you're planning to finish your calculus sequence back at your home campus, and you don't want to pay for this book, I guess you can not, but I would suggest at least you rent it or something like that, just so you'll have something to do. Unless you've already bought your book for at your home campus, what you're going to use in the rest of your calculus. If you've done that, you can use that. I taught from many calculus books, and just about all of them, the table of contents are so close, they're almost identical. A few chapter numbers different, or arrangement different, and the order may be a little different, but the same topics are hit. So if you have another book, you can certainly use that. Just do the homework exercises from that book, okay, not from this one. But if you are going to get this one, let me tell you what this one provides. I don't like the publisher, Cengage. I don't particularly care for them. But what they do, 100% free, it's on the back of the book here, internet resources at larsoncalculus.com. They'll have interactive examples, okay, and periodically I'll point these out. Thus and so is found at larsoncalculus.com. And here's Devin. Okay. Now, every now and then I have to go back and check because my cord, I noticed it started doing this over the weekend. The cord sometimes doesn't maintain good contact and it starts running on battery and my battery is not good. Okay, so larsonprecalculus.com, an absolutely free website. Okay, your grandmother can go to larsonprecalculus.com. She doesn't have to be enrolled in the course. There's no charge, no access code, nothing. Anyone can go to it and follow that. There are videos there. There are three-dimensional graphs. There are videos with Bruce Edwards, who's the second author of the text, and editable, not editable, but editable spreadsheets. Okay? Now, let's move on to your homework assignments. At the end of each section, there's homework problems. The odd numbers have answers in the back of the book. So I always assign odd numbers so you can check your answers. If you can't get the answers that's back there, see if you can figure out how to get it. If you can't figure out how to get it, don't get frustrated. Don't say, I have to wait until Monday to find out how to do this problem. No. Go to calcchat.com, another absolutely free website. Anyone can go to it, no code required. Go to the website, and they will have solutions to the odd number exercises from the text. When the solutions are not enough, they can chat with an online tutor for live help, but you'll have to figure out the tutor's availability. Okay? But, in addition to that, certain of those odd number problems, not all of them, but a few scattered here and there, are found at calcview.com. Okay? And that presents video solutions of selected exercise from the text. You can watch calculus instructions, progress step by step through the solutions, providing guidance, blah, blah, blah. So, the one reason I like this book is the author. Okay? And he has great stuff there. So even if you don't buy the book, you can still get you can use those online helps without the purchase of the book. Now, ultimately, I haven't done this yet, and I hope I'm not going to run out of time. I think I'm going to have to contact Cengage, the publisher, and get them to set up WebAssign for me, because I don't use WebAssign, but if those of you, and by the way, and this is all explained in the syllabus and in the YouTube video when I talk about the syllabus, one thing Cengage does do, they just started this year, they provide the Cengage Unlimited that for $119 a term, $120 a term, really it's closer to $119.99, okay, $120 a term, you have access to the book, the ebook, and then WebAssign, which is a homework, online homework, program. I don't assign things through that because we got plenty of good homework here, but in order to access the ebook, you have to have a code, and I'll give it to you. You get it free for so long. Does anyone know how long? Anyone using that?
Maybe 40 or 30 days.
Second?
Maybe 40 or 30 days.
Yeah, something like that, which is going to be half the term, but you know. But I'll try to get the WebAssign set up soon. Again, it's in my stack of things to do. But if you want to go that route, or any of you also taking physics this term here at Lawson, okay, that book is also a Cengage book, so for the same $120, you get this one and that one if you want to do that. But you don't have to, it's up to you, okay? Now, if you want a hardbound, not hardbound, if you want a paper copy of the book, it'll be loose leaf, you know, but hard copy, but not hardbound copy, for another $8, I think, you can order that. You can rent that. It's not purchased, it's rent. Is yours rented or? You actually purchased yours, okay. So you can also do that. And $8 is not bad, but it's just a rental, okay.
Well, I rented mine for $40.
Okay. Yeah, and you can rent it, which did you use? The bookstore or somewhere else?
Off Cengage.
Oh, off Cengage, okay. Just straight from Cengage, or did you go through the bookstore? Straight from Cengage. So you can rent the book as well, and you turn it back at the end of the term. Are you a Lawson student, or are you a?
No, I'm a trainer.
You're a trainer student. Okay, so yeah, you'll use the one you go when you go back home. Okay. So there's lots of options there. There's rental things through the bookstore. There's rental things through online. There's several good rental things, and even Cengage itself will rent to you. Okay. Anything else that might be beneficial to you? Any of you others have questions? Okay. So if you'll catch up through the YouTube videos. And while I was doing that, I lost my place, but I'll find it back pretty quickly. I don't do anything very quickly, so I'll find it, but it'll take me a bit. There we are. Okay. Any questions, anything we've done so far? All right. We talked about squeeze theorem last time, but we didn't quite get to, and also the squeeze theorem is sometimes called the sandwich theorem or the pinching theorem. I've never called it the pinching theorem. I've heard it called sandwich theorem before. I like the idea of sandwich, but that's because I like to eat. But anyway, one more, and this is theorem 1.9 here, two special trigonometric limits. Okay? Now, we talked about basically polynomial limits. I think that's most of what we've talked about so far. The first chapter, by the way, is on limits. And if sometimes I'm a little shady on what we covered and what we haven't, I'm doing all three calculus courses Mondays and Wednesdays this term. So what I've said in one class, I can't remember if I said in another. But anyway, here are these two special trigonometric limits. Nice to know. The limit of sine x over x. Okay, now if you think about this, sine x, okay, as x is approaching 0, and I don't have much room to write on here, but I'll try to write here, okay? That's not a very good horizontal line. Sine x goes something like this, okay? Right? As x is approaching 0, of course, sine x is approaching 0, right? 1 over x, as x is approaching 0, 1 over x is approaching 0. Now, if I were to plot 1 over x, give me a color, some different color from the one I just used. Pick a color, any color. Green, okay. There, we'll do it in green. Here's what 1 over x looks like. Looky there, folks. The ratio of that to that, as x is approaching 0, almost the same function. And that would be 1. That's how I remember this. I don't memorize it. It's just I think of the graphs, and they have the same slopes. We haven't gotten the slope yet, but we've been talking about them. They're almost the same slope, so therefore the ratio is going to be 1. And sure enough, it is. Okay? Now, this isn't a proof. This is just the graphical aid to help remember this. Okay? And we'll be using that later, I promise you. The second one of these is the limit of 1 minus cosine x as x approaches 0 over x. And they say that one's equal to 0. So let me delete these two. I'll keep my same ugly graph. Okay. I'll even try to delete that point there. I'm going to blow it. Look at that. Okay. And let me go back to dark. And let me just sketch in cosine for you here. Something like that. So 1 minus cosine would be something like that, right? If you do 1 minus cosine, that would give you a 0 here, and then you'd be positive on either side because it's 1 minus this value would be slightly positive, 1 minus that side. So it'd be something like that, right? Not exact, and it's not going up forever. That was poor, but it does something. Well, I'm not going to get into all how it does, but that's basically what it's doing. All we're interested in is near 0, okay? And of course, 1 minus cosine x is 0. The limit, as you get closer and closer to 0, that's going to be 0. But here is your, again, you want to use green again or a different color? Green, okay? Here is your 1 over x. See, the other issue here is I've had this computer years, and one time the hook on this chair happened to catch the connection from the computer to the plug in the wall here, to the projector here, catch it, and when I moved the chair, it pulled the computer onto the floor, and it landed just about like that, okay? So now there's some sort of a short here that's close, well, this is connected here, and when this moves, that's close enough to here. There's something in it that's just not right. As my younger brother used to say, it ain't right, and so every now and then it'll flop off, and usually it'll come back on, and this time has chosen not to. So let me do what I can to see if I can make it come back on. Sorry, I shouldn't have been flopping it around like that. There we go. All right. Most of the time it comes back. See if that's better. Okay. And we've lost. Now the power is doing the same thing. So there's so many things. I think that's okay for now. All right, so anyway, let's look at this. Well, here, this is approaching 0 and stays pretty close to 0. As 1 over x approaches 0, it's leaving 0 pretty quickly. So it looks like to me the 1 minus cosine wins, and sure enough it does. So the numerator stays close to 0, the denominator leaves 0 pretty quickly, so that one, the limit is 0. You don't have to, this is just hand waving here. That's how I remember, this one's 0, this one's 1. These two slopes are almost the same thing, so the ratio of that ratio, okay, is the ratio of that, those limits as you're getting close to 0 is very close to the same thing. So that's going to be 1, that one will be 0. Okay? Hang on to those. As I said, you will need them later, like next chapter. All right. So why don't they throw another trig function that's not covered in the theorem here? How in the world are we going to find that limit? Any ideas? Okay. Any idea? Did I hear someone mumble something? A little louder.
Plug it in, put it in zero.
Plug what in?
Zero.
Okay. Oh, okay, yeah, okay. Always a good first step. And by the way, for people who weren't here before, that is a very good idea. Plug it in, okay? And if you plugged in here, what you would have would be tangent of 0, that's supposed to be a 0, over 0, which is not usually a very good thing to have because you can never divide by 0, but, and this is what we talked about before, unless your numerator is also approaching 0. And what is tangent of 0? 0. So this is one of those indeterminate forms. Ha! So this one is something that still has possibility of having a limit. If this had been 7 over 0, no limit exists, it will never exist. But if you have something that's 0 over 0, there is a possibility. It may have no limit, but it is. So that let us know we have an indeterminate form, but it doesn't give us the answer. But it's a good first step. We do know now that it is a indeterminate form. And here's Jemiah. I know you're in here, but trying to hide on me. There you are. Okay. All right, good deal. And I think I've gotten everybody else here. I'm only missing Jabril and Taiwan, and they haven't been here from the beginning. So, oh yeah, and Michael Dwayne Bell. No, none of those three have been in the beginning. So all who have been here are here. Perfect attendance. Way to go, folks. Keep it up. All right, so since plugging in confirms that we can continue, it's a 0 over 0 case, but it still doesn't give us a limit. How can we proceed to find the limit? Any ideas?
Factor.
Factor. How would you factor that? Great idea. How would you factor it? Okay, I'll factor x. You can't factor it. Okay, it's prime. How about tangent x, though? What is it? Okay, we're going to have a limit as x approaches 0 of, did I hear a sign? Yes, there's a sign there. Did I see a sign? No, I didn't see one, but okay. Sine, say again. Oh, come on, trig scholars. Over cosine. Okay, so what I'm going to do is I'm going to separate that and put the over cosine over here. There is method to my madness here, folks. And here I'm going to put the over x part. Now, why would I do something silly like that? Because what's this limit? 1. All right, remember? That was sine over, yeah, okay. That's 1, and what's the limit of cosine as x approaches 0? 1 also. So this will be 1, and that would be 1 over 1, which is 1. Perfect. So this limit is 1. Okay, good deal. Make sense? All right, let's see how they did it. Direct substitution yields the indeterminate form, 0 over 0, just like we did, always a good first step, okay? To solve the problem, you can write tangent as sine over cosine. They remember their trig much quicker, okay? And obtain the limit, and notice what they did, clever them. They spread the sine over cosine like this and put the 1 over x over under sine, because now we know this is limit of 1, and we know this is 1 over 1, which is a limit of 1. So that gives us, indeed, the limit as sine of x approaches 0 of sine x over x is 1 from that theorem we just did. And this one, just by plugging in, 1 over cosine of 0 is 1, and that's 1. So both of those limits are 1. So then you get the limit of a function, which is a multiplication problem, is the multiple of the limits. Okay? So it's the product of the limits. And that limit's 1, that limit's 1, 1 times 1 is 1. Good deal. Make sense? Any questions? All right. Here's a figure that kind of shows that, okay? And if you're surprised that's how tangent over tangent look, well, let's think about it just for a moment here. Tangent in the fourth quadrant, which is the one over here, that's negative, but 1 over x is also negative, so that becomes positive. And then first quadrant, positive over positive, that's positive. So sure enough, that's pretty much how it looks. Now again, it goes to infinity here and here. No limit as you approach negative pi halves or pi halves, none whatsoever, because that's one of those discontinuities you're never going to overcome, okay? Because 1 over cosine as x goes to pi halves, not ever going to exist. That will be a 1 over 0, not going to happen. And 1 over minus 0 is not going to happen either. So it has limits anywhere in here, but not there and there. Okay, make sense? But we are approaching 0. Sure enough, it approaches 1. Do I graph anyone I'm doubtful about? No, it's way too much work. But if you have a graphing calculator and know how to use it, by all means do that. You'll probably get some visual help there. Any questions? Whoa! They have that being the last. And they do have a little proof for that special trigonometric limit. And it's really a pretty nifty little proof. And any of you who are math majors, probably worth your effort to spend a little bit of time with that. And by the way, let me go on and mention this as well. You'll see scattered throughout the book these little QR codes. And when you see those, you can take your phone and do on it, and it'll take you straight to that calcview.com, and you'll hear more and see more calculus professors or author or somebody is going to explain that a bit more, and probably will go through the proof with you on this one. Okay? So again, this book has a lot of features, and any hard copy of the book, you can do a QR code on. So even for $40, or if you do the whatever, any way you get a copy of the book, you can probably benefit from that. Okay, we did example 9. They didn't do example 10, so let's back up and do example 10. Okay? And we'll do that right here. A limit involving a trig function. Here is find the limit, okay, as x approaches 0 of sine of 4x over x. Whoa. All right. How would you proceed on this? Second? I heard something, but my hearing's really bad.
Approaching 0 or negative.
This is limit is x approaches 0 of sine x over x.
Plug in 0.
Plug in 0. Good idea. What do you get here? 0 over 0. Indeterminate. So we know two things. We can eliminate two things. Number one, it doesn't have a fixed limit that you would get if you plugged in and got 7/14. You'd be done. But we don't. But it also doesn't give you 7 over 0, which has no limit, or negative pi over 0, has no limit. Anything else over 0, no limit, we'd be through then too. But this is 0 over 0, which means it's indeterminate. We're not sure whether the limit exists or not, so we got to do a little more work, which we love doing, right? Yes, okay. Now, what do we do from there? Oh, divide by 4. Okay? Well, if I divide by 4, I'd better also do something else. Multiply by 4. Why? What's 4 over 4? 1. And guess what? I can multiply by 1 anytime I want to. Doesn't change the value at all. Dividing by 4 is going to change the value. Okay? But multiplying by 1 will not change the value. Okay, now what do we have, folks? Okay, this 4 is nothing but in the way, so let's pull that out. A constant can be pulled outside of a limit, okay? Okay, and what do we have left? Sine of 4x over 4x. Wonder what that is. That's 1 for sure. You can think of that as sine of u over u as you approach 0. Yep, that's 1. So this will be 4 times 1, which is 4. Let's see how they did in the book. Good for them, they got it right. Okay. Any questions? Make sense? All right, good deal. That now finishes, finally, 1.3. Now, some of you are new. I'll hold this up as long as I can. My homework assignment here would do any of the odds, 5 through 21. The reason I say odds, their answers are in the back of the book. If you can't get the answer in the back of the book, see if you can figure out how to get it. If you can't figure out how to get it, don't get frustrated. Go to, up here at the top of the page, see calcchat.com for interactive help and worked out solutions for the odd number exercises. So if you can't get the answer in the back and can't figure out how to get it, go to calcchat.com. Now, number 7 here is in red. Okay? That means this QR code will take you straight to number 7. If you got a cell phone, take a picture of the QR code. It takes you straight to calcview.com, or you can go there by hand if you wanted to, and you'll find number 7, and it'll explain how to go from there. Okay? I'm not going to hold the book up for all those. So do any of the odds that you choose, as many as it takes for you to say, hey, I got this down, move on to the next. Then do either 23 or 25. They're both a Calc Chat. 25 is a Calc View. Do any of the odds 27 to 35. They're all a Calc Chat. 29 is a Calc View. Do either 37 or 39 or both. They're both a Calc Chat. 39 is a Calc View. Do any of the odds 41 to 45. They're all a Calc Chat. 43 is a Calc View. Do any of the odds 47 through 61. They're all at Calc Chat. 53 is at Calc View. Do any of the odds 63 to 73, they're all at Calc Chat. 65 is at Calc View. Do any of the odds 75 to 81, they're all at Calc Chat. 75 is at Calc View. Do any of the odds 83 to 89, they're all at Calc Chat. 83 is at Calc View. Do 91, it's only at Calc Chat. They don't have it at Calc View. Either 93 or 95, they're both at Calc Chat. 97 is an exploring concepts. If you want to take a look at that, you can. Hopefully it's at Calc Chat as well. I haven't checked to see if it is. 99, sort of a writing exercise. I would at least think through that, and you might find some help at Calc Chat. There's a free-falling object problem that is very familiar to you who may be taking or will be taking physics. That's 101. You can do that one if you would like, and then based on that, you can do 103, and they both should be at Calc Chat. Finding functions 105 should be at Calc Chat, and the bunch of these are proofs then, okay? And if you're into proofs or they help you understand, or if you're a math major, you may want to take a look at any of the odds 107 through 111. You can think about doing 113. They should all these should be at Calc Chat. And then there's some true false. Don't expect to see true false on a test, but these problems will help you think through the problems to see if you can figure out why they're true or false, whatever. So that's 105, any of the odds 105 to 115 to 119. Okay? Number 121 is another proof. 123 is a graphical reasoning. They should both be at Calc Chat. Any questions? Okay. So then let's move on to second? Probably. Okay. Moving on to 1.4. Someone chomping at the bit to get the first task. Good to hear. Okay. All right. Here's 1.4. When we finish 1.5, that'll be test time. And we're getting close, folks. Okay, as long as these classes are in the summer. And some of you are looking at that and saying, Aren't these classes a bit too long? You're absolutely right. But we have administrators who don't understand math, and they say, oh, no, our classes are too short in the summer. They were about a few minutes, so they moved them 25 minutes longer. Way more than a few minutes, okay? So we got plenty of time, and guess what? We charge you the same low rate, okay? So aren't you fortunate? So let's pick up here with current slide. All right. Chapter 1 is limits and their properties. 1.4 is continuity and one-sided limits, okay? In this section, we'll be determine the continuity at a point and continuity on an open interval. We'll determine one-sided limits and continuity on a closed interval. We'll use properties of continuity, and we'll understand, of course you will, and use the intermediate value theorem, a very handy-dandy theorem. So let's start with continuity at a point and on some open interval. Okay? Now, in mathematics, the term continuous has much the same meaning as it does in everyday language usage. Okay? Limits kind of have the same thing too. Other things sometimes are way off, especially when you get into physics. You talk about velocity and speed. You talk about those interchangeably in everyday language, but when you get to physics, velocity is always a vector and speed is always a scalar. So there are some differences, and there will be in math too. But this is just about the same. Informally, to say that a function is continuous at c, at some value x equals c, means there is no interruption of the graph at f to c. As f's going along here and approaching c, it continues just like you would expect it to. That means it's continuous at c. That is, the graph is unbroken at c, no holes, no jumps, no gaps. Okay? Well, I'll explain what we mean by that. This figure illustrates it. This figure illustrates or identifies three values of x at which the graph of f is not continuous. At all other points on the interval a to b, when it says an interval, that's always the independent variable, the x, the horizontal axis, okay? On a to b, the graph of f is uninterrupted and continuous at every place else except on this one at c. Now, there's a couple things they're showing here. Every one of these intervals, a to b, they are what we call open intervals. What do I mean by that? Anyone know? The parentheses here and the little circles here mean that it's defined everywhere inside between A and B, but not necessarily at A or at B. Maybe, but it doesn't have to be. So that's what we call an open interval when you have parentheses. If you had a bracket on one side, the other side, or both, that means you identify your function on one side, the other side, or both. Okay? But when it's parentheses, that means an open interval. That's not in the problem yet, but we're going to get to it later. Okay? Now this one, f of c is not defined. Okay? And we already had an example of one like this. Remember when we did our factoring and dividing out a common factor? That left a hole in the graph. That's sort of like this one showing right here. Okay? That's how you would get a hole in the graph. It's not defined at x equals c. Everywhere else it is defined, and it's continuous everywhere else, but it's not defined at x equals c, so it's not continuous there. Here, it is defined at x equals c. There it is. There's a value there. But at x greater than c, it jumps down and goes here. So this is continuous here and continuous here, but not continuous here because it jumps from here to there. That's called a jump inequality. This is called the hole in the graph. This is called a jump inequality. Okay? Now, here's another rather strange case. The function is defined at c. Over here it wasn't. No definition for it at all at c. Here it is defined at c, but it's not where you would expect it to be. There's still a hole in the graph up here. Even though it has a function at c, this is still discontinuous at c. because it's tooling along here, continuous everywhere, and then all of a sudden jumps down here again, just for one point, and then jumps back up here and continues tooling along. Okay? That's discontinuous at C. It can be discontinuous at C because it's not even defined there. It could be discontinuous at C because it has a huge jump in the whole graph, or it could be discontinuous at C even if it has a value at C and otherwise would be smooth and continuous. It's not because it's not where you expect it. So those are three different ways that it can be discontinuous at some value C. Okay? Now, by that figure, it appears that the continuity at x equals C can be destroyed, boy, that's strong, isn't it, by any one of the following conditions. If the function is not defined at C, how can it be continuous at C? If the limit of f of C does not exist at x equals C. Now, we haven't quite defined that yet, but I don't think we have anyway. Again, I teach you so many courses. Okay. The limit, let's go back to the graph so I won't be arm waving here. The limit as x approaches C here would be this value right up here. There would be that y value there. That says x approaches C from the left. As x approaches C from the right, however, here would be the limit. And those two limits are not the same. And if the limit from the left is not the same as the limit from the right, the limit does not exist. So that's what we mean there. And that's what they mean here. The limit of f of x does not exist at x equals C. Even though the function is defined at x equals C, right and left does not. Why not? Or the limit of f exists at x equals C, but it's not equal to f of C. And that's what we have here. Okay? The limit as x approaches C here is this value. The limit as x approaches C from the right is also that value. So the limit exists, but it's not the same as the function value. So that would be another discontinuity. Okay. So those are the three cases in which the continuity can be destroyed. Okay. If none of the three conditions is true, the function f is called continuous at C, as indicated in the following important definition. Continuity at a point. A function f is continuous at C when these three conditions are met. Number one, f of C has to be defined. If it's not defined, no, it's not continuous at C. Okay? The limit as x approaches C of f of x exists. So f of C is defined and the limit exists. Okay? That has to happen. That means right and left hand limit exists. But number three is also required that the limit as f of x, it not only does it exist, but it must equal f of C. If it doesn't, when you plug in the C, like that one that had the dot out of place, that limit doesn't exist. So continuity on an open interval, that's one in parentheses where the ends are not necessarily defined. A function is continuous on an open interval, a to b, those are x values now, when the function is continuous at each point in the interval, okay? And the function that is continuous on the entire real number line from minus infinity to positive infinity is everywhere continuous. And we have certain functions that are there, and they're beautiful, wonderful, nice functions to deal with. Yes?
Just because a function is defined, does that mean that the limit exists?
Okay, say that one more time.
If f(x) or f of c, if it's defined, does that mean the limit of f(x) exists?
Okay, that's one of the three conditions that it would be. First, it has to be defined. If f of c is not defined, the limit can't possibly exist, because you've got to be able. So that's just one of the three. But not only that, see down here, the limit must also exist. Even if it's defined, the limit must exist. And what's more, not only must it exist, but it must be the same value as f of c. So all three of those are required. Okay. Now, consider an open interval that contains a real number c. Oh, this is I. I was thinking that was a slant. That's a italicized I. Consider an open interval I that contains some real number c. If a function f is defined on that I, except possibly at c. function f is defined everywhere on I except possibly at C, and f is not continuous at C, then f is said to have a discontinuity at C. So this is sort of the negative side of it. Discontinuities fall into two categories. One is a removable discontinuity, and the other is non-removable. Okay? A discontinuity at C is called removable when f can be made continuous by appropriately defining or redefining the f of C. Let's go back here. This is discontinuous because f is not defined at C. If you say that's the value of f at C, we're just going to take it and say here's the function f, but we're going to combine that with this value right here when x equals C. So it'd be f everywhere that x is not equal to C will be here, and x equals C, we're going to redefine or say that's its value there. That would be removable because you can just plug in a value right there. Okay? This one, there ain't no way you can make that continuous. There's no value you can give a C that ever going to make those meet. Not going to happen. Okay? So this is non-removable. This one, however, is removable because we can redefine and say, no, we're not going to have that equal here. We're going to move it up here and have that be our value at C, redefining that, and then that would be made to be, that would be a removable discontinuity. This one would be removable. That one's never removable. Okay? Not removable. Okay? All right. A discontinuity. Let's see, blah, 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 blah. Yeah, we just said that. Hey, and here they are again. I didn't know they were going to do the same three over here. For instance, the functions shown back there are removable. This one's removable. That one's removable. Because everywhere else, the limit exists. If you just redefine, or here define f of C equal here, it's not defined in this original thing. Just add a, piecewise, function here. Say it's whatever this is up here, and down here it's going to be that value x equals C. Then that would be continuous. This one will change this and say it's not, because this function was defined here with f of C being this. We're going to say, no, let's change it and make f of C that. That's removable. This one, there's nothing you can define here that's ever going to make that continuous because the limit from it's non-removable discontinuity. Make sense? Okay. So let's discuss the continuity of each of these functions. What do you think about A? Is it discontinuous anywhere? Oh, it's continuous everywhere, huh? What's its value at 0? Say again? Undefined, okay? Can't be continuous everywhere. It's not even defined at x equals 0. Okay, so it's not defined there, so therefore it must be discontinuous there. Is that a removable discontinuity? How? Okay, how would you define it as 0? Okay, let's think about this a moment. As x approaches 0 from the left, from the negative side, it's doing something like that, right? As x approaches 0 from the right, it's doing that, right? Now, where are you going to redefine? It's going to connect something that's going infinitely far down here from the left, infinitely far up here from the right. How are you going to combine that? Yeah, not going. That's non-removable discontinuity at x equals 0. Any other value of x? Continuous. No sweat at all. None whatsoever. Anywhere else. But at x equals 0, discontinuous, irremovable, non-removable discontinuity. How about G? Is that continuous everywhere? Second? Okay. How about x equal 1? Got a problem, don't we, Houston? Because 1 minus 1 is 0. Can't divide by 0, can we? Okay, so it's going to be not defined at x equal 1. But what can we do with this one? We've done it before. What could we do here? Factor. Sounds like a capital idea. Okay. How would we factor that numerator? X plus 1 times x minus 1, and the denominator is x minus 1, and then guess what happens? Notice the sound effects there? We eliminated the x minus 1, and we got this is x plus 1. So that's a good old straight line function, isn't it? Slope of 1, y-intercept of 1, going like this, except the x equal 1, you got a hole in the graph, don't you? Because you can't have x equal 1 because the original function did not allow that. Okay, so it's discontinuous at x equal 1. Continuous everywhere else, but discontinuous at x equal 1. Is that removable or non-removable? Removable. How can we make it removable? How can we make it continuous? Define x equal 1. G would be defined to be what? Plug it in, plug it in. High-level math. 1 plus 1 is? 2! Didn't know you'd be doing such hard math today, did you? Okay, 1 plus 1 is 2. Okay, so if you redefine this function here, this function not defined at x equal 1. But redefine it for x. Okay, this new function is going to be g of x, which is x squared minus 1 over x squared, x minus 1, everywhere except x equal 1. But the new function is going to be defined, it's equal to 2 when x equal 1. Then, yes, that new function will be continuous everywhere. All right. Now, how about this one? Shucks, look like I'm going to have to graph this and those. Oh, maybe not. Let's see. Where would be the possible place this would not be continuous? So this is x plus 1 for every x less than 0. That's continuous everywhere, right? X squared plus 1 for every x beyond 0, right? Greater than 0. So that's defined everywhere. Where's the only possible? Yes. Add x equals 0. What is the value here? 1. What's the value here? 1. That's going to be continuous everywhere. Because even at the place where you might suspect the discontinuity, it has the same value. So that's continuous everywhere. Now, it's a sort of strange-looking function, if I can draw strange-looking functions. Okay. Here is what it's going to look like less than 0, and that includes the 0 there. Now this one is going to be like this. Only that one is not defined at x equals 0, but guess what? It's the same function there. Straight line on this side here, but it has the same value here, whether it's coming or going to the left or right. So yeah, that's continuous everywhere. I'm going to introduce a new term here. It's not smooth everywhere, because this is coming up like this, and that's going like that, so it's not smooth there, but it is continuous there. Okay. How about this? Y is equal to sine x. Any ideas? Continuous everywhere. Okay, sine x is this, like this forever and ever and ever and ever and ever in both directions. It just keeps doing that. So this is continuous from minus infinity to infinity. This is continuous from minus infinity to infinity. This is by itself discontinuous at x equal 1, but you can make it continuous everywhere by defining at x equal 1 the value is 2. Then that becomes continuous everywhere once you define that. This one, discontinuous at x equals 0, no way to remove that discontinuity at all. Okay? That's our talking about it. Let's see how they do it. The domain of the first one, this is 1a, is all non-zero real numbers. Okay? Defined for negatives, defined for positives, but not defined at 0. And from theorem 1.3, you can conclude that f is continuous, that every x value in its domain, except it's not defined where it's not in its domain. Okay? And here's 1.3. This is a flashback to the past. If P is a polynomial function, and C is a real number, then the limit as x approaches C of P of x is P of C. But that's for polynomial functions. This is not, 1a is not a polynomial function. It's a rational function. So you go down here. If R is a rational function given by R of x is equal to P of x over Q of x, yeah, 1 is a polynomial function, which is 1. That's a constant function, 1. Q of x, x is a polynomial function, x, okay? And C is a real number such that Q of C is not equal to 0. Ha! There's the kicker. Q of 0 is equal to 0. So at that value, it's not defined. So the limit as x approaches C of R of x is R of C whenever, which is P of C over Q of C, as long as C is not 0. Q of C is not 0. And if x equals 0, it is. So that's not defined at C equals 0. That really doesn't seem to help too much, but on the other hand, it does. So at x equals 0, this is a non-renewable, removable discontinuity. Because this one, I wish they'd have shown it better, goes like this forever, okay? And this one goes like that forever. X equals 0, never. You don't get the one going down this way that equals one going up this way. Just not going to happen. Non-removable discontinuity, x equals 0. Continuous, all here, continuous, all there, not continuous at x equals 0, and non-removable. So the graphs help, or at least the picture of the graphs, your mental image of it. In other words, there's no way to refine alpha 0 so as to make the function continuous at x equals 0. No way at all. The B part, that is the domain of G, is all real numbers except x equal 1. Okay, that was the one that had an x minus 1 in the denominator. Okay, from the theorem, you can conclude that G is continuous at every x value in its domain except x equal 1. That's not in its domain. And that is the one that was a good old hole in the graph. Okay, because this is the graph of x plus 1 at every value except x equal 1. Not there. Okay, so at 1, 2, this one is not defined. Okay, so it's discontinuous there, but it can be made continuous, a removable discontinuity, by redefining the function, a new function, to be 2 when x is equal to 1. G is not defined at x equal 1, but you can define a new function to be 2 at x equal 1. So by redefining G of 1 as 2, the redefined function is continuous for all real numbers. Okay? This is the one I sort of drew, and you see that almost looks like mine. This is a function that's x plus 1 for all x is less than 0, x squared plus 1 for all x is greater than 0 except 0. But those have the same value at x equals 1. I mean at x equals 0, value of 1. So those are continuous. Not smooth, but continuous. Okay? And this is the D one here. 1.6 we did last time before we did the limit of sine x as x approaches c is sine c. That's good everywhere. Everywhere. As is cosine. Tangent, where is tangent not defined? Anyone remember? Say again.
Zero.
Oh, no, it's defined as 0. Tangent 0 is 0. It's the half pies. All the half pies. Pi has 3 has pi, 5 has pi, 5. Negative half pi, negative 3 has pi. All your half pies not defined. Because there your cosine is 0 and tangent is sine over cosine. You can't do it. How about cotangent? At the whole pies, okay? I like whole pies, okay? Those are at 0, pi, 2 pi, negative pi, all those whole pies. That's not defined. Everywhere else is defined, okay? How about secant? half pi's again, just like tangent. This is 1 over cosine. So anywhere cosine is 0, secant not defined. Just like tangent is sine over cosine, anywhere cosine is 0, tangent's not defined. How about cosecant? Whole pi's again, okay, because that's 1 over sine, just like cotangent is cosine over sine. So wherever your denominator is 0, those are not defined. Good deal. All right, and here was your sine function defined everywhere. Everywhere, negative infinity, positive infinity. Just keeps on going. Cosine does the same thing. It's just same shape, just shifted pi halves. Okay. Defined everywhere. Continuous on the entire real number line. Entire domain. Minus infinity to infinity. All right. Let's see if we skipped anything. We did 1. Okay, this is page 76. One side of the limits in continuity here. Okay. Good deal. Now, I know this is a long class, close to 3 hours. I know many of you may have eaten breakfast and rehydrated. So if at some point you get so uncomfortable that you can't focus, let's take a stop and take a break, okay? I call them bladder breaks, so you can call them anything you want to. But if you need to, let me know. All right. All right. Continuing. One-sided limits. To understand the continuity on a closed interval, you first need to look at different type of limit called a one-sided limit. For instance, the limit from the right, or the right-hand limit, means that as x approaches c from values greater than c coming in from the right, okay, like here, x is approaching here, x equals c, but x is approaching c from the right, this has a limit right there. That's the limit, okay? And that you identify that as the limit is up as x approaches c from the right. The little superscripted plus there means it's coming from the plus side of c, okay? Of f of x is L. Now, this one's a real easy one because it's left or right, it's a L, you know, so, but this one is, that's it's still a true statement. The limit of x approaches c from the right of this function f of x is going to be that value L. Also, f of x is your y value everywhere. I used to tell my pre-calculus algebra class that one thing to remember about pre-calculus algebra, one idea, hang on to the tightest, y is equal to f of x. Okay, so your f of x value here is your y value there. Okay, f of x value there is a y value there. Here would be there. So remember that f of x equal y. Y is equal to f of x. Okay, so got that. Similarly, the limit from the left, as x is approaching here, here's f of x here, as x approaches c, f of x is again approaching L as c approaches x from the left. Okay, and here's how we identify that: the limit of as x approaches c from the minus side, from the lesser side of c of f of x is L. If those two limits are the same, the limit exists at c. Okay. And obvious, there's a closed thing there. But even if there was an open circle here, the limit would have still been this, and the limit would have still been that. So the limit exists at x equals c. This one is obvious because it's defined that way, but the limit doesn't exist. One-sided limits are useful in taking limits of functions involving radicals. Okay? For instance, if n is an even integer, and you're taking the nth root of x, okay, as x approaches 0 from the right-hand side, that's going to be 0. How about if x approaches 0 from the left-hand side? If n is an even integer, 2, 4, 6, 8, 10, whatever, okay, what would that be? Undefined. You can't take the even root of a negative number. You can't take the square root of negative 3 or negative anything. It's not defined. Third, cube root, yeah, no sweat. Fifth root, 17th root, no sweat. 16th root, no way. Okay? Not if this is negative. So as x approaches 0 from the positive side, this is 0. because the nth root of 0 is 0, no matter how you're approaching. But you can't approach it from this side because it's not defined over here at all. Okay? Just like x, 0 in the denominator is not defined, negative numbers under even root not defined. But from the right-hand side, it is defined, and it's defined to be 0 as x approaches 0. So how about this? What's our problem child here? Or children, maybe. Where would we tend to have problems?
The square root.
Okay, yeah, there's a square root.
If x was negative.
Say again?
If x was negative.
If x was negative, negative 1, this way. Right? 1 minus a negative 1 squared is 1. 1 minus 1, 4 minus 1 is 3, square root of 3. It's an irrational number, but it's no problem.
So I'm saying, like, if x was greater.
Oh, if what's in here is negative, that's exactly how you need to think about it. Okay? What you can say here, since this is an even root, okay, now when, this is, I'm sure, a pretty basic review. If you don't see a coefficient, what do you assume the coefficient is? 1. Okay? If you don't see an exponent, what do you assume the exponent is? 1. Okay. If you don't see an index on a radical, what do you assume that it is? 2. This is the only place that a missing number is assumed to be 2, not 1, and that's on a radical. The index of that radical is 2. That's the square root if you don't see anything. If you had a 3 in there, that'd be a cube root, no sweat anywhere. If you had a 16 here, yeah, you're in the same problem with the 2, okay? So since that has an index of 2, even though you don't see the 2, what we say to ourselves is 4 minus x squared has to be greater than or equal to 0. It could equal 0. It can't be less than 0. That's exactly what you do when you see a radical sign. If that index is even, then you have to say this. That thing that's inside there has to be greater than or equal to 0. Can't be negative. Okay? Now, you can do this algebraically, or you can sort of just think through it. Which way you want to go? We love algebra, don't we? Yes. So let's do it algebraically. What can you do with this thing right here? Factor. All right. How would that factor? Okay. 2 minus x times 2 plus x. It doesn't matter which order you do, but put the 2 in front. That product has to be greater than or equal to 0. By that? Yay or nay? Okay. Yay. Okay. Now, here we have a product. And it says the product has to be greater than or equal to 0. In other words, sort of positive, right? Any product, what determines its positivity or negativity? Negativity. Or something like that. What determines? Signs. How? What's the rule of a product? Okay, if there are different signs, this thing's going to be negative. If they're same signs, it's going to be positive. So the only way this product is going to be positive is if both of them are positive or both of them are negative. Okay, so this is true when 2 minus x, which we want to do first, positive or negative? Tell me, somebody. Anybody? Positive, okay? Greater than 0, greater than or equal to 0, and, that's not an or, and 2 minus x. I don't need the parentheses, greater than or equal to 0, okay? So let me take out the parentheses, okay? But now, I'm going to put an or 2 minus x less than or equal to 0, and 2 minus x less the 2. This is the plus here. What are y'all doing? You're letting me get away with that? Okay. Greater, less than or equal to 0. In both of these cases, this thing is going to be positive, right? If both of these are positive, that's going to be positive. If both of these are negative, that's going to be positive, right? So what we do now is figure out what values make this true. Okay? Can we solve that first little inequality here? What would we do? Subtract 2 from both sides of the inequality. That's good. What would that give us? Negative x is greater than or equal to negative 2. Okay? Now that would be hunky-dory if we didn't have the minus sign there. So how can we get rid of the minus sign? Multiply or divide by negative 1. Okay? What would the left-hand side become? X. The right-hand side would become 2. What goes in between? Anybody? Aha! You're absolutely right. Anytime you multiply or divide a directional inequality by a negative number, adding or subtracting doesn't change it. Multiplying or dividing by a positive number doesn't change it. But multiplying or dividing by a negative number flips the inequality. So this says x has to be less than or equal to 2. Okay? What does this one give us? Subtract 2 from both sides, and that gives us x is greater than or equal to negative 2. And both of these, or either of these has to be true. So what I like to do on this is draw me a number line. Okay? And I'm going to put my 0 somewhere in the middle. And if that 0 in the middle, I'm sorry, I got it too low. There's 1, there's 2, 3, 4, 5, 6. And negative 1, negative 2, 3, 4, 5. Okay. So here, there's my 0 in the middle. There's my negative 2. And it says here, x has to be greater than or equal to negative 2, or less than or equal to positive 2. And that would be here. So guess what? There we have it. Anything between x equal minus 2 to x equal plus 2, inclusive. That's going to make this positive, right? All right, let's do the same thing down here. Okay, subtract 2 from both sides. That goes to 0. You get minus x is less than or equal to negative 2. And then what could we do? X is greater than. Okay, y'all let me get away with something else there. I messed up here. I thought I was doing what I say. This was an and here, and the or is between these two. Okay, so this had to be that and that, so you were limited to between minus 2 to plus 2. Okay, this is an and here, so either x has to be greater than or equal to negative 2, and when you do this over here, subtract 2 from both sides, and what does that give you? X is less than or equal to a negative 2. Now, can you give me an x that's both greater than or equal to 2, and that is a positive 2. I don't know what that spot is there, but it's not anything important. Okay. I need an x to be greater than or equal to positive 2 at the same time and be less than or equal to negative 2. Nothing fits that bill. These x's are out here, these x's are over here. Nothing in common. So this produces absolutely no viable issues. So this is the only interval over which this is going to be true. Now, it says find the limit of f of x equal to that as x approaches minus 2 from the right. Well, here's your minus 2 as it approaches it from the right. What is that going to be? As x approaches minus 2 from the right, that would be going to zero. Yeah, because plug in a minus 2. Minus 2 squared is 4. positive 4. 4 minus 4 is 0. That's approaching that from the right. From the left, not defined because these values aren't even included. Okay? As x approaches positive 2 from the right, guess what? Those values are not included. They're not in the domain of your f. But as x approaches positive 2 from the left, yep, that also is going to 0. Okay? So, there we have it. Does anyone know what that would graph as? Second? Okay. Here's just a little hint. What did I say f of x is equal to? In pre-calculus algebra, it's always equal to y. Y is equal to the square root of 4 minus x squared. Okay? Now, what could you do to make that look a little neater? What is the ugly thing about that expression? The square root sign. Yeah, that's pretty ugly. How do you undo a square root? Square both sides. So this will become y squared is equal to 4 minus x squared, right? Okay? Now, let's get our variables on one side. So what would we do? Add an x squared to both sides. And you get x squared plus y squared is equal to 4. What does that describe? Anybody? A circle of radius 2. Exactly. So that would be that. And there's the positive side of that. And here's the negative side. There's your circle of radius 2. And guess what? Not defined out here, not defined over here, only defined in between the two. Well, of course, that's not a function. Since you don't have the minus here, this is just a semicircle, the top half of the circle. And that's exactly it. So as x approaches negative 2 from the left-hand side, sure enough, that's approaching 0. As it approaches positive 2 from the, I said that wrong. Approaches negative 2 from the right-hand side, that's approaching 0. Approaching positive 2 from the left-hand side, that's approaching 0. Approaches positive 2 from the left-hand side and the right-hand side, no, it can't because it's not even defined out there. Same here. As it approaches negative 2 from the left-hand side, can't. It's not defined out there. So, yeah, you got a semicircle. The top half of that circle. Isn't that ugliness? Never mind. Okay. Let's erase all this mess, okay? And let's see how the book does it. Ah, they do the semicircle too, okay? It's shown in the figure, the limit as x approaches negative 2 from the right-hand side is 0. As it approaches from the left, it doesn't approach it from the left-hand side. It's not defined out here. As it approaches positive 2 from the left-hand side, that's 0. But it can't be defined here because it doesn't ever exist out there. Sure enough, that's it. The graph sort of helps you see it, but you can do it algebraically. And so as x approaches negative 2 from the right-hand side, the plus side, sure enough, that's 0. Now, one-sided limits can be used to investigate behavior of step functions. Y'all know what step functions is? Are? Those are functions that look like you can walk up them, up steps. One common type of step function is the greatest integer function. Greatest integer in x. Y'all familiar with this one? Ran into it before? Not? Okay, it's defined to be, now it has sort of a double bracket is what I call it. Almost is like two absolute value signs, but it's not. It's a double bracket. That means the greatest integer, n, such that n is less than or equal to x. Okay? So, what's the greatest integer in 2.5? 2, yeah. The greatest integer n that's less than or equal to that. That would be 2. 3 would be too much. Okay, that would be 2. How about the greatest integer in negative 2.5? Negative 3, very good. What you do, here's how I picture this. Find 2.5 on the number line, look to the left, that's the less than or equal to, find the next integer there. Okay? Now if you're sitting right on top of it, that's it. But here at negative 2.5, look to the left, the next integer is negative 3. So yeah, that's it. Good deal. Does that make sense? Yeah.
Why was it only half a circle?
Well,
Could you explain why it was only half a circle? Like the
Oh.
you did.
Okay, you're going back to this one. Okay? Okay, now what if it were a whole circle here? Okay, would that be a function? Functions have to pass the vertical line test, and that would. So it'd be a function only if it intersects only once. That's one reason. The second reason is if you don't see a sign in front of a radical, you assume it's a positive principal square root, meaning the positive one. If you had a minus sign there, then that would have been the lower half. Okay? So that's the other clue. One clue is there's no minus sign in front, and the other is that if you did have a complete circle, it wouldn't be a function. You have great relation, but not a function. Answer? Okay. All right. Now, so they just sort of left you hanging there. Let's see what they're going to do next. And the limit from the left is not equal to the limit from the right. The two-sided limit does not exist. Next theorem makes that more explicit. Now, it just feels like to me they left off something here, did they? Yeah, they did. They left off example 3. So let's go back and do example 3. Find the limit of the greatest integer function, f of x, equal to greatest integer. I don't draw this well, but something like that. As x approaches 0 from the left and from the right. Okay, so we want the limit of greatest integer of x as x approaches 0 from the left. That would be from the minus side, and we want to find the limit as x approaches 0 from the positive side, from the right, of the same function. Okay? Now, they suggest, and I think probably it's a good idea, is draw the greatest integer function. And that's what I thought. I couldn't believe they told you about it and never drew a picture of it. So you're going to help me draw it. Okay? I'll do the axis part. Don't worry about that. I've got it done. And I'll even put the values in. 1, 2, 3, 4, 5, 6. Not very even, but okay, and we'll go up here 1, 2, 3, 4, 5, 6, 7. Okay, down here 1, 2, 3, 4. Okay, something like that. Okay, now help me draw this. Give me an x. Second, 1. Okay, what's the greatest integer in 1? 1. All right, we got it right there. Give me another x. 6. 1, 2, 3, 4, 5, 6. Okay, out to the limit here. What's the greatest integer in 6? Yep, you got it. Right there. Okay. Give me another x. Second? -1. Greatest integer in -1 is? -1. There, we got that one. Next. Anybody? Anybody? Help me. Negative what? 3, okay. -3, what's greatest integer in -3? -3. I think y'all got the integers down pat, right? It'd be -2, -2, -4, -4, -5, -5, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. You got the integers. There they are. Okay, they're all there. Give me something not an integer. Give me an x. 1/2. The greatest integer in 1/2. 0. Oh, I didn't even put my 0 in. So that would be 0. Okay, good. Another non-integer x. Second? A little louder. 1.5, okay? 1.5 would be here. What's the greatest integer in 1.5? 1, okay, got it. Anyone got an idea where this is heading? Why is that? There we go. Second? I can't hear. Okay, so what it is, it's a line that is all along here because the greatest integer anywhere there is going to be 0. Because look to the left, that's the next integer. But when you get here, you jump up to here. And then you go flat here until you get here, and you jump up, well, wherever it is. I have it in the wrong place. There's 2, 2, and that goes along here, and then it jumps up here. 3, 3. So you see the general picture. Mine is not very good. Okay. Open on this end, closed on this end. Closed on this end, open on this end. Closed on this end, open on this end. Closed on this end, open on that end. You see the idea? Down here, same deal. Closed here, open here. Closed here, open there. Closed here, open there. They're all integers. Your y values are all integers. Your x values are any real number. Okay? And you see why they call it a step function. Looks like you're going up steps. Okay. So, the limit is x approaching 0 from the left-hand side of greatest integer in x. X is approaching 0 from the left-hand side. What's its limit? Here's x to the left. What's its limit? Minus 1. Down here, from the left. From the right, it's 0. From the left, though, it's negative 1. So this will be negative 1. This will be 0. So it's discontinuous at the integers. Okay? Every integer. It takes a step up. No way to remove that discontinuity. That's it. Non-removable discontinuity, all the integers. Continuous everywhere in between the integers, but discontinuous at the integers. Continuous everywhere between the integers, discontinuous at the integers. Make sense? Okay. And I think that's what they have here. Yep. Got it. Any questions? All right. Now we're ready to move to existence of a limit. See someone leave? I thought I sent some. Yeah, someone did. And we're right at about midway through the class. You want to take a potty break? I just want to move around, but I do want to take a bladder break myself. So I'm going to put this on hold. Sorry, my throat's awfully scratchy. All right. Any questions on anything we've done so far? Okay. So we talked about one-sided limits. So now let's see how that connects with continuity on the closed interval. When the limit from the left is not equal to the limit from the right, the two-sided limit does not exist. That's sort of those situations that you got two values coming in different ways and you can't make them fit. You know, irreplaceable, irremovable discontinuity. So theorem 110 then sort of reverses that and says the existence of a limit, let f be a function and let c, I can't talk, c and l both be real numbers. Then the limit of f of x as x approaches c is L, is that limit L, if and only if the limit as x approaches c from the left is L, and as f of x approaches c from the right, that same limit of f of x is L. So they have to be the same. For instance, that one, that was a linear function here and a quadratic function here, since it ended at the same point, that limit existed. Okay? If it had done something like this or that, the limit would not exist. So this is what tells you what happens even if you have functions that are not the same, but if they have the same limit coming from left or right, then the limit exists for the entire function. Okay? The concept of a one-sided limit allows you to extend the definition of continuity to closed intervals. Basically, a function is continuous on a closed interval when it's continuous on the interior of the interval and exhibits one-sided continuity at the endpoints. That is stated formally in the following definition, or next definition, and that's this one. A function f is continuous on the closed interval a to b. Notice the brackets here now. That means we're including the endpoints. When f is continuous on the open interval a to b, it's got to be that. To be a continuous on closed, it has to be continuous on open. And at the same time, the limit as x approaches a from the right-hand side, a being the lesser limit, so approaches a from the right-hand side, is equal to f of a, and as x approaches b from the left-hand side, the limit as that happens is f of b. So then you can color in the dots here. See, before we had an open circle here because we weren't sure what was happening at the endpoint. But if this is f of a here, and the limit is this is f of b here, if that would be the same on both, then it's continuous from the right at a and from the left at b. So now that's what we call it, continuous on a closed interval. Okay? Doesn't seem very earth-shattering. I mean, so what? Whether it's open circles or closed circles, pretty much the activity is going to be the same. So discuss the continuity goodness gracious, of alpha of x equal the square root of 1 minus x squared. Okay. This should, yes.
Not continuous if x is greater than 1.
And what about, it's not continuous if x is greater than 1? Absolutely correct. Okay? Okay? So x cannot be greater than 1. Okay? By that. Anything else? Second? Did you say lower one? I couldn't hear. For people who've just gotten here, people who were here before I said this, I'm hard of hearing. I'm, really badly hard of hearing, so I don't hear well. So if I ask you to repeat something, it's not you, it's me. I can't hear. So what did you say? I heard something, but I couldn't make it out. Okay, help me somebody. What else? We know that it's not even defined for x greater than 1. Anything else you can tell me about it? Boy, this is similar enough to stuff we just did. I thought someone would jump all over this. Say again? I hear noises, but I can't make it out. Huh? What's that? Factor it? Ah, okay. What you're doing is looking at the inside here. And what we're saying about the inside here is that 1 minus x squared, what about it? It's got to be greater than or equal to 0, right? That's what I thought you said. Okay. All right. Has to be positive because you can't take the square root of anything negative. So what's under that radical has to be greater than or equal to 1. Anyone tell me what's going to come out, or do we have to work our whole way through it? You said factor it. We can factor it. What would that be?
It would be 1 plus x and 1 minus x.
That product has to be greater than or equal to 0, right? Okay. Does it look close enough like anything we've ever done before? Please say yes, okay? What do you think the bottom line is going to be? We already know x can't be beyond 1. Can't be greater than 1. What you reckon else? Nobody, huh? Didn't we do something awfully close to this before? What was the bottom line there? Okay. X can equal -1. That's perfectly fine, because if x is equal to -1, then you have what inside there? Second? 0. Okay, so the square root of 0 is 0. So f of -1 is equal to 0. Okay. What else can you tell me? F of +1 is 0. Okay. Now, do you think f can ever be negative? You reckon so? Because you say, that's a radical there. We always assume the principal square root, which is meaning positive. So here we have sort of the endpoint. X equals -1, f of -1 is 0, f of +1 is 0. Guess what's going to be in between? It can't go here, so what do you reckon? I'm guessing it can't go here either. So our whole domain is between these two. And we know that's defined here and here, so we do have a closed interval from -1 to 1. How about in between there? Is it defined there? Sure, because anything in between these, let's say a value like zeros in between +1 and -1, that's defined. That would be 1. 1/2 would be 1 minus 1/4. Yeah, that's 3/4. 1 minus -1/2. That would be 3/4. Yeah. Everything in between these two is defined. Someone want to hazard a guess what shape that would be?
It would be the half circle.
Half a circle. That's going to be your semicircle from -1 to 1. And it's going to be 1 right up there. So yeah, it's a circle of radius 1, but it ends right here and it ends right here. Okay? So that's on a closed interval from -1 to 1. So it's continuous on the closed interval -1 to 1. Not defined less than -1, not defined greater than +1, but it is defined in between, but including the endpoints. So yeah, the closed interval from -1 to 1. Make sense? Awfully close to that same one we had before with square root of x squared, 4 minus x squared. That was plus or minus 2. Okay. All right. That was quick and dirty. We didn't go through all the gory detail, but I know you remember how to do that. The main of this is the closed interval from -1 to 1. That's exactly what we said, including the endpoints. Okay? At all endpoints on the open interval -1 to 1, the continuity of valve follows from theorem 1.4 and 1.5. 1.4 was the n is a positive integer, the limit the value for any time valid. Let n be a positive integer. The limit below is valid any time when n is odd, and is valid only for when c is greater than 0 and is even. That's greater than 0. Well, we found that is defined at c and at minus c, so now we can include the endpoints. So 1.5, the limit of a composite function, if f and g are functions such that f limit, this is a review, this is stuff we hit last time. The limit as x approaches c of g of x is L, limit of x approaches L of f of x is f of L, then the limit as x approaches c of f of g of x would be the limit of, would be f of the limit of as x approaches c of g of x, which this limit is L, and F of L is that. Okay, which to me is almost a circular logic there, but yeah, it is correct. And you might say, what does that have to do with this? Well, that whole thing can be put to things. So, moreover, the limit as x approaches -1 from the positive side is going to be 0, and that's going to be L of -1. And limit as x approaches +1 from the negative side, +1 from the negative side, that's also going to be 0. That's going to be, and that is F of 1. So therefore, it's continuous from the left. This means it's continuous from the left here, from the right. I said it back. From the left here, from the right here. That's what I was doing. From the right here, from the left here. So it's continuous everywhere in between, including the endpoint. So it's continuous on the closed interval -1 to 1. So they said it. They went through a whole bunch of stuff and came back and said it again. Make sense? And it's a semicircle. Okay. Now, it looks like to me they're skipping example 4 and 5. Okay, so let's go back and do. No, we just did 4. I'm sorry, that was the one we just did. So they're skipping 5. So, whoops, let's do 5 here. Okay. This is on page 78 if anyone's following. Charles's law and absolute zero. This isn't my law, this is a guy whose last name is Charles. On the Kelvin scale, absolute zero is a temperature 0K. And this isn't physics, but I'm just going to tell you. On the Kelvin scale, okay, the scale we're used to using is, Fahrenheit. On the Fahrenheit scale, when we mention a temperature, we always put a little degree symbol. 90 degrees Fahrenheit. That's what it's supposed to get up to today. It's probably pretty close to it now, okay? Some of you who are from more progressive countries, you may use what scale? Celsius scale. And what do you use when you're talking about a Celsius temperature? A degree sample, okay? It might be probably 35, 36 Celsius, something around there, okay? Degrees Celsius. When you're on the Kelvin scale, do not use a degree symbol, the number K. So they said 0K, they didn't mean 0 degrees K, it's 0K. Never use a degree symbol with the Kelvin scale, the absolute scale, absolute temperature scale, okay? Although temperatures very close to 0K have been produced in laboratories, absolute zero has never been attained. Okay? In fact, evidence suggests that absolute zero cannot be obtained. Okay? Now, I have actually read either in a physics or a physical science book, they can get within a few millionths of a degree of absolute zero. And my question is, what kind of thermometer can you use that you know you're within a few millionths of a degree and that you're not over? I mean, what kind of thermometer is that precise? I don't know the answer to that, okay? But that's absolutely true. In fact, what was just stated was the third law of thermodynamics. The third law of thermodynamics says absolute zero can be approached but never reached, okay? Now, that's what we understand now. And it kind of makes sense, okay? Now, in the old days, before quantum mechanics was around, they thought all motion stopped at absolute zero, and therefore you couldn't get there because motion can't stop. Molecular vibration cannot ever stop. If it did, everything collapses, basically. So they said you can approach absolute zero, but you can't. Well, when quantum mechanics came along, they said, whoops, there is no absolute stop. There is basically a zero reference level. It doesn't mean motion is stopped, meaning it's in its lowest energy state possible. Okay, so then in quantum mechanics, they said you can approach the lowest energy state possible, but you can never attain it. Basically, is how they changed that. So you can approach absolute zero, but you can't ever attain it. Third law of thermodynamics. Now, who knows? It may be proved false someday, but so far, yes. Now, here's what they did. French physicist James Jacques Charles, that's where it gets its name, he discovered, and here's basically what it was. And I think most of you probably would agree to this. I give the example, when I was doing graduate school, my last graduate school, I was up in Lincoln, Nebraska. It gets kind of cold up there in the wintertime, okay? It gets cold here too, but not as cold as it gets up there. And there was a lady from our church who had a son. They were, she and her husband were divorced. The husband moved to another town. So the kid, he was a real great kid, didn't have a male role model, and she was begging men from the church to sort of come and do things with him. So he had an idea. I thought, I'm single. I've never had kids. I would not be a good fit for this. Until he came out and played on the church softball team. I was playing too. I was no good whatsoever. He was a really good athlete. I thought, and because he was young, he didn't know what to do with all these old guys, so I was kind of befriended him, and helped him out. So, and we got to getting along really well. I said, maybe this will work. So we started doing things together. So I went over one Sunday afternoon. It was beginning to be cooler weather. He left the basketball out all night, okay? And he said, oh, I must have punctured the basketball. It's sort of flat. We're going to have to get a new one. I said, no, take it inside. He said, what will take it inside? I said, just take it inside. So he did, where it was warmer inside. And let's do something else for a while. I don't know what we did. I said, go check the basketball. He said, don't you remember it's flat? I said, go check your basketball. He went in, and sure enough, it was fully pumped up now. What had happened? In the cold, it lost volume. In the warm, it expanded. Because what happens with temperature is it's the average kinetic energy of molecules. And when the molecules have more kinetic energy, meaning a higher temperature, that means they bounce around harder and faster and bounce on each other and bounce on the surface, so they take up a greater volume. Well, this is what Jacques Charles found out. He was measuring a variety of gases, okay? You take one gas and raise it to some temperature and measure its volume. So let's just imagine the horizontal scale here is the temperature scale, and the vertical scale here will be a volume scale. And he was probably using Celsius. I don't know. I'm guessing he was using Celsius. And at some temperature here, the gas had a certain volume. And then as he lowered the temperature, the volume of the gas went down. Lowered the temperature, it went down. Lowered the temperature, it went down. Actually went past 0 Celsius, and lowered the temperature, the volume went down. Kept lowering it, and the volume kept decreasing. But at some point, he got it so cold, it became a liquid. It condensed to a liquid. And then its volume went almost to 0. But all along that, it was within experimental error, a very good straight line. So then he did a different gas. And that different gas, volume here, volume there, volume here, and kept going down. And at some point, it became a liquid, and the volume went almost to 0. And he did another gas, and it was here, here. We found out that every one of these lines, they were all straight lines, but they had different slopes, but they all pointed to a common value. They never got there because they became liquid before, but the slope, if you extrapolated the slope, they all went to the same point. He said, hey, that's where it would go if the volume went to 0, which of course it couldn't. A gas, I mean, if you have at least one atom in there, it's not going to have a 0 volume, but if it did, that would be absolute 0. And that was the other reason that you could approach absolute 0, but you couldn't get there because the molecules would all be in there, and it can't actually go to 0. So anyway, that was your physics lesson today. That was Charles's law, not mine, but somebody else's. Okay. Now, so what he did he did these various temperatures here, and you see it in a table, and I don't want to write the table, and not many of you have books. A few of you do, but I'll sort of hold this up. People at home, sorry, you need to come to class, but all of you are here, or at least, except for the ones who haven't made it back from break yet. That was the reason I sometimes don't like to give breaks, but I needed one. Okay. All right. Okay. He did a variety of temperatures here and measured the volumes very carefully and plotted these things, and sure enough, look at that, following a straight line down here. Now, at the time he was doing it, he probably couldn't get much below minus 40 Celsius, which is pretty dadgum cold, okay? It is really, really cold. Nowadays, we can get lower than that, and they kept going and kept going, and sure enough, the extrapolation of that was about negative 273.15 degrees Celsius. Well, in absolute temperature, that would be 0 Kelvin. Okay. But what he did when he was doing these and got these points that you see in the table here, plotted in this graph here, what they did was did a linear regression on those, and then that gave you to 4 significant digits there, and looks like 6 significant digits there, and it came out to be something that approximated negative 273.15. Okay. And then they did a different gas. No, it looks like the same table. I don't know why they repeated the table. Okay. Oh, I know. They didn't repeat the table. They put Fahrenheit degrees there. And guess what? It came out to the same temperature. Different temperature Fahrenheit, but it was the same temperature. Okay. And I don't know what they expected you to do with the problem there, but they did. So that'll be enough for that. All right. Hardly seems worthwhile erasing the board, does it? So let's move on to properties of continuity. Here we go. This is the top of page 79. All right. Let's assume we have B as some real number. Now, usually it's the right-hand limit of our interval, but we're not sure that's what it is here. Let's just let B be a real number. Let f and g be 2 continuous functions at x equals c. Okay, they're both continuous at x equals c. Doesn't say anything about anywhere else, but they're continuous at x equals c. Then the functions listed below are also continuous at x equals c. Now remember, b is just any old real number here, not necessarily our right-hand end of the interval. In fact, definitely not that. Okay. B is any real number, f and g are continuous at some value c. Scalar multiple says if you multiply this function f, which you know is continuous at c, by any real number b, positive, negative, fraction, decimal, rational, irrational, it doesn't matter, any real number b. As large as you want it to be, as tiny as you want it to be, multiply it by b, then b times f is still a continuous function. Okay? Second is some are difference functions. F is continuous at c, g is continuous at c, then any sum or difference of those two functions will be continuous at c. So the scalar multiple is continuous, the sum or difference are continuous. The product function will be continuous at c. F multiplied by g will be continuous at c. The quotient function will also be continuous at c, f divided by g, as long as g of c is not 0, because you can't ever divide by 0 still. So as long as g of c is not 0, then the quotient function is equal to 0. So what this is meaning is you can do all these normal operations with functions, and if they're continuous, the new functions are also continuous. So, it summarizes the functions you have studied so far that are continuous at every point in the domain. Polynomial functions continuous everywhere. So guess what? Multiply this by a constant, it's still continuous. Add it to another polynomial, still continuous. Subtract it from another polynomial, still continuous. Multiply it by another polynomial, still continuous. Divide it by another polynomial, as long as that other polynomial is not zero at that value you're doing, it will be continuous. Okay, rational functions is exactly what we just said. The ratio of two polynomial functions, as long as that denominator is not zero, that will be a continuous function. Now here's the kind of the new one. The radical take the nth derivative, nth root of any old function of your variable x, and this will be a continuous function as long if n is even, as long as your x is greater than or equal to 0. Okay, can't be if it's less than 0. If n is odd, x could be anything. Okay, your trigonometric functions, sine and cosine, continuous everywhere. In fact, these are all continuous at every point in their domains. The secret is where are the domains. This one can't be negative if n is even. Okay, to be negative if n is odd. This continuous everywhere, no matter what the x is. These tangent and secant, as long as x is not a half pi. Cotangent and cosecant, as long as x is not a whole pi. Everywhere in their domains where they're defined, so is their continuous there.
You said polynomial.
Polynomial is continuous everywhere, always. Positive, negative, negative, positive. Rational functions, except where the q is 0. Okay, so the discontinuity is there. This one, if n is even, then anywhere x is negative. Discontinuous there, no values there. If n is odd, continuous everywhere. And the trig functions, these are continuous everywhere. These are continuous except at the half pi's, and these are continuous everywhere except at the whole pi's. Now, by combining the theorem of 111, which we just did a short list ago with this list, you can conclude that there's a wide range, variety of elementary functions that are continuous at every point in their domains. So you can multiply a polynomial by a sine or cosine continuous everywhere. Okay, you can do a rational function times a radical function as long as this is met, and if this is n is even, these are not negative. So you can mix, match, add, subtract, multiply, divide, as long as all the domains stay legitimate. Okay. So here's example 6. By this theorem, the one we just did, it follows that each of the functions below is continuous at every point in its domain. Why do you put it in an example if you tell you what the answer is? Okay, sorry about that. Is this continuous? No. Polynomial functions are continuous. Sines are continuous. Sum of any continuous functions are continuous. At what values? All real numbers, because this polynomials are continuous, all real numbers, and sines and cosines are continuous, all real numbers. This one, is that continuous? Except where tangent is not. This is a polynomial, simple, 3, okay? So multiply is fine, except when this is not defined. Where is tangent not defined? Half pi's, exactly. So everywhere this is defined, 3 times that is defined, okay? How about this one?
X equals 0.
Second?
X equals 0.
What about x equals 0? Is that defined or not defined? Oh, yes it is. Cosine of 0 is defined. Cosine of 0 is 1. So yeah, that's fine there. Where's cosine not defined? Cosine is defined everywhere. But what can you not have in a denominator? 0. And where is cosine 0? Not it. Okay. Where is cosine 0? defined because that's sine over cosine. It's a half pi equal cosine pi. So that's defined everywhere. It's continuous everywhere except at half pi's. Because that's where your denominator would be 0. Okay. Make sense? All right. Here's theorem 112, continuity of a composite function. If f is if g is continuous at c, f is continuous at g of c, then the composite function given by f composed with g of c, which is defined to be f of g of c, f of g of x, I'm sorry, is continuous at c. If g is continuous at c and f is continuous at g of c, then g of f of g of x is continuous at c. Throwing in our little composite. Okay. So here's example 7. And again, here it says, describe the intervals on which each of these functions are continuous. Where is tangent continuous? Except what? Half pi's, exactly, okay? All real number x as long as x is not a multiple. Pi has plus or minus n pi, okay, plus n pi. Where is this continuous? Now remember, we're saying continuous here. Where is this one continuous? It's really continuous everywhere because this is not defined, but it just keeps getting bigger and bigger and bigger, or smaller and smaller and smaller, you know, and sine is defined everywhere, so this is defined everywhere except at 0, because this thing right here is not defined at 0, and if you assign a value at 0 here, does this make this continuous? Not really, because remember what this was doing? The closer you get to 0, it's equivalent. Up and down, up and down, up and down, between plus, minus, minus 1. Faster and faster, 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 but never rest at anything. So defining this at 0 doesn't make that continuous. So this will never be continuous because this is not defined. So don't ever expect it to be. Uh-oh. This is a weird one, okay? Certainly that's not defined, okay? Just like we were saying before. But the expression x times the sine of 1 over x, and here's what I'm going to do. X is 1 over x. Would you agree with that? Yay or nay? You wouldn't. Okay, except for x equals 0. Obviously, that's not going to work. But give me another x, not 0. Any x. Just make up an x. Huh?
If it was 1, it would be 1.
Okay. If you make it x equal 2, that would be 1 over 1/2. What is 1 over 1/2?
2.
2. So if x is 2, x is 2. So these are the same. Try any other number except 0. 0 will never work. But any other number that'll work, right? So then rather than writing this that way, we could write this as the x here is 1 over x times sine of 1 over x, right? Which would be the sine of 1 over x over 1 over x. And if you made the 1 over x something like u, it'd be sine u over u. What would that be?
Sine of u.
Huh? Sine u over u as x is approaching 0 would be 1, right? We had that one. Okay? If we just put that in, that would be that, and as x is approaching 0, this approaches 1. But this is going to 0. So that's not going to be continuous. Okay? Even though you can't do this in the first place and you run into problems, if you could do it, and that would be approaching 1, this is going to 0, so that would not be continuous. So this would be continuous everywhere but x equal pi, any half pi. This would never be continuous, ever, at x equals 0. Any other x would be fine, but not x equals 0. And this would not be continuous at x equals 0. Now that's my guess. Let's see what they do. The tangent function is undefined, all your half pi's, so pi halves plus n pi. All other points is continuous. That's what we said. This one, oh wait, so this is the graph of it, okay? So it's continuous everywhere except that the half pi's and the half pi's never continuous, ever. One's going to positive infinity, one's going to negative, okay? So it's continuous everywhere it's defined, just not defined there. Okay, because y is equal to f of x is continuous except x equals 0, and the fine section, the sine function, the fine function, whatever, is continuous everywhere. It follows that y is equal to sine of 1 over x is continuous all real values except x equals 0, and that's exactly what we said. Never continuous there. Now, you can't graph it because the closer you get to 0 on either side, the faster this goes up and down and up and down, up and down, up and down, up and down. You know, the closer you get to 0, it just does faster and faster and faster, but it always stays between that. It's not ever defined anywhere. It's just between -1 and 1. From the left and from the right, coming the same way. It's continuous from negative infinity to 0, but not counting 0, and from 0 to positive infinity, but not counting 0. Okay, so everywhere except x equals 0. Okay, now the C part, its oscillations are damped by the factor of x, and they say it's continuous everywhere. I kind of wanted to disagree with that, but I guess what they're saying here, if you draw it this way, you see it is getting closer and closer to 0. But again, the limit of that, as x is approaching 0, doesn't seem like that would be 0. It seems like it would be 1, but obviously it's not 1. It is 0. So they say it is continuous everywhere. I just have a real problem ever letting that get close to 0. Can't happen, but the x multiply that 0 times, well, yeah, here's the other thing. This thing right here is always between plus or minus 1. This is arbitrarily close to 0. So yeah, that is going close to 0. So I'm sorry, I messed that one up. That is going to 0. If you did your, whatever you call that, envelope function, whatever they have names for that. All right, let's see if there's anything else here. I'm sorry, I should have said this earlier. Let's go back to example 6. Okay, this is example 6. This is one place I said I would say it, and then I skipped right over it. This is example 6. See larsoncalculus.com for an interactive version of this type of an example. Remember I said that early on, larsoncalculus.com. You can go and they will talk in gory detail about anything you want to hear on example 6. Okay? And example 7 we just did, and they have those pictures in the book. So now we're ready for the intermediate value theorem. All right. 1.13, an important theorem concerning behavior of functions that are continuous on closed intervals, which was what we were talking about before. called the intermediate value. If F is continuous on some closed interval A to B, that means everywhere between A and B and including A and B is continuous. No holes, no gaps, no discontinuities. And F of A at this end is not equal to F of B at that end. It could be here and here. It just can't be there and there. They can't be equal to each other. K is any number between F of A and F of B. So if F of A is down here and F of B is up here, K is anywhere in between. If F of A is up here and F of B is down here, K is any number in between. Any number in between F of A and F of B. Now, so here we have a continuous function on the closed interval A to B. Continuous. F of A is somewhere here, F of B is here, or vice versa. K is some number in between these two values. Then it says there is at least one number C somewhere between A and B, okay, such that F of C is equal to K. In other words, you can't get from here to here and not pass here. You can't have it because it's a continuous function. It has to somewhere be that K in between at some number C. Maybe more than one C is doing this. Yeah, it could be 15 in between there, or any number in between there. But there's going to be at least one where F of C is equal to K. If it's continuous, it's got to be. Now, this intermediate value theorem tells you that at least one number exists, but it doesn't tell you what the number is. That's another problem. It does not provide a method for finding the C. Such theorems are called existence theorems, and therefore, to me, they would be the hardest ones to prove. Okay. Proof of this theorem is based on the property of real numbers called completeness, and that's what you have to use. The intermediate value theorem states for a continuous function of F, if x takes on all the values between A and B, then F of x must take on at least all the values between F of A and F of B. So you see why you can't have F of A equal F of B. That then doesn't tell you anything. There's no values in between here that would have to be. So there can be something like this or something like that and have nothing to do with either one. Okay. As an example of the application of the intermediate value theorem, consider a person's height. So just consider how tall you are right now. Okay? A girl is 5 feet tall on her 13th birthday, and 5 feet 2 inches tall on her 14th birthday. You know, in between her 13th birthday and her 14th birthday, she was every height in between 5 and 5'2". She was 5'1" at some day in there. She was 1.5 in some day, 1.75, 5.1. Yeah, every height in between 5 feet and 5.2. At some day in between those times, she was one of those heights. Every day, okay? Because she didn't suddenly wake up one morning having jumped, and skipped the height. She couldn't do it. So for any height h in between 5 feet and 5 feet 2 inches, there must have been some time t when her height was exactly h. Now, when you get old like me, you start getting shorter. Actually, you do. Because the spacing between your vertebrae, the cushioning that's in there, it tends to flatten out some, so you actually get shorter. So at some point, probably I reached my maximum height somewhere since it has been declining. So every day in between then and then. Now, I was every height in between there. I haven't changed much, but probably did change a little bit. It seems reasonable because human growth is continuous and a person's height does not abruptly change from one value to another. It can't. It is a continuous function. Okay? The intermediate value theorem guarantees the existence of at least one number C on the closed interval A to B. Okay? That sentence doesn't really make a lot of sense. I mean, it's certainly true, but what? There may, of course, be more than one number C. So, yeah, I've already said that. Okay. I think they left something out here. They left out for any value K, or whatever they said. They just left that out with that sentence. There may, of course, be more than one number C, such that F of C is equal to K. It's shown here. Now, human growth doesn't quite go like this, but a lot of things do. Profit margins, things like this, they can go up and down and stuff like this. So there may be more than one point in between A and B where F of X is equal to K. Okay? That's okay. There's got to be at least one of those because it's a continuous function. Let's see. What bugs me that sentence is not a very good sentence. But this picture is in my text, so oh yeah, that one is. I guess in context it makes sense. Okay. But here, if it's a discontinuous function, you can't use intermediate value theorem. The given in the intermediate value theorem was F had to be continuous. If F is not a continuous function, yeah, you could easily have a K somewhere in there in between the two places where it is discontinuous. So intermediate value theorem does not work unless the given function is a continuous function. Goodness gracious, those lights are flashing like that. It's not me, is it? Okay, good. I was going to say. So I'm about to have a migraine or something because I'm seeing lights do this. Okay. For example, this, I think we beat that dead horse. Okay. So it's all right. Any questions? You might say, okay, why? Okay. Intermediate value theorem often can be used to locate zeros of a function that is continuous, on a closed interval. Specifically, if F is continuous on A to B, and F of A and F of B differ in sign, one's positive, one's negative, vice versa, whatever, then the intermediate value theorem guarantees there's at least one zero on that, if F is a continuous function. For instance, a polynomial function, continuous always, okay? Then if you have F of A being negative and F of B being positive, or vice versa, F of A positive, F of B negative, there's got to be at least one zero in between A and B. So, use the intermediate value theorem to show that the polynomial function F of X equal X cubed minus 2X plus 2X minus 1 has a zero on the interval 0 to 1. How would you show that it does have a zero there? Plug in the 0, plug in the 1. Okay, I put it in the wrong place. What is F of 0? Negative 1. What is F of 1? 2. Okay, that'd be 1 plus 2 would be 3 minus 1 is 2. Guess what? Intermediate value theorem, since this is what kind of function? Polynomial function. It's continuous everywhere, including between 0 and 1. Everywhere between 0 and 1, including 0 and 1. Closed interval there. So, since it's negative here, positive there, there's got to be at least one 0. Does that tell you how to find the 0? No. It just tells you it exists, an existence theorem. What would you do to see if you could find what it was? Second? Plug in. I'd say plug in a 0.5. Calculate that, see what it is. It's either going to be negative or positive. If it's negative, then go something between those two. If it's positive, do something between those two. You keep doing that. That's the hard way, the easy way. Do it on your graphic calculator and let it calculate. Okay, but there are simpler ways to do it, but that's one way to do it. All this tells you there is a 0. Okay. It's an existence theorem, not a how to find theorem. Okay. Don't let me run too far over because I got another class starting just 5 minutes after this one. Note the f is continuous because it's a polynomial function on the closed interval 0 to 1, and that f of 0 is -1 and f of 1 is 2. Follows that there has to be some place in between 0 and 1 where f of x is equal to 0. Okay? Now, they did it graphically here. They still don't tell you what the c is, but here it's 0 minus 1, here it's 1, 2. There's got to be at least one place. And because this doesn't vary that greatly, it's not going up and down any times, it's just going straight through there. Still don't know the value. Now, there are techniques, and maybe by the end of the course, we'll have that technique. Sorry, I didn't get the good door open. Okay. All right. But it just tells you there has to be some value in between there at 0. Okay? Now, what I was just describing is called the bisection method for approximating the real zeros. Okay? As in that last example. If you know 0 exists, which we did, then take the point in between. I said 0.5, that's exactly what we did here. We know what f of 0 is. Figure out what f of 0.5 is, or 0.5 is 1. Okay? If there's a sign change here or here, one of the two, there's got to be. Okay? Then determine which interval contains a 0. If the sign changes between here, go to 0.25. If it's here, go to 0.75. You know, just keep bisecting, repeatedly bisecting the interval. You can close in on the 0, whichever way it's going, and get it to as much accuracy as you want. Now, this wasn't what it was originally called, but this would be one of the techniques I would call the method of exhaustion. Okay? You're never going to find exactly the value. It's going to be an irrational number more than likely. So you can close in until you get whatever precision you want. 3 decimal places, 7 decimal places. You can keep going until you get it as close as you want. And then you say, I'm tired, that's close enough, I'll stop there. Okay. Whoa! And they stopped there, didn't they? Let's see if there are any more examples here. Nope, that was example 8. So we did finish 1.4. Homework exercises here would be any of the odds 5 through 9. They're all at Calc Chat. 5 is at Calc View. Any of the odds 11 through 29. They're all at Calc Chat. 11's at Calc View. Either 31 or 33 or both. They're both at Calc Chat. 31's at Calc View. Either 35 or 37 or both. They're both at Calc Chat. 35's at Calc View. Any of the odds 39 to 57, they're all at Calc Chat. 47's at Calc View. Any of the odds 59 to 63, they're all at Calc Chat. 61's at Calc View. Any of the odds 65 to 69, they're all at Calc Chat. 67's at Calc View. Excuse me. Any of the odds, either 71 or 73, they're both at Calc Chat. Neither of those are at Calc View. Any of the odds 75 to 81, they're all at Calc Chat. 83 or 85, they're at Calc Chat. 87, it's at Calc Chat. Any of the odds 89 to 93, they're all at Calc Chat. 95 to 99, they're all at Calc Chat. 95's at Calc View. You can explore doing 101 and or 103. They should both be at Calc Chat. True, false, any of the odds. Sorry. Sorry, I'm losing my voice. Any of the odds 105 to 109, they're all at should be at Calc Chat. 111 you can think about doing if you'd like, and 113's a data plan. They both should be at Calc Chat. Oh, there's more. Yay. All right. 115 should be at Calc Chat. 117's a proof if you're interested in doing that. 119 you could do. 121 was something similar to the absolute zero problem. 123. Making a function continuous by a proper choice of values. 125 is similar, so either 123 or 125, they both should be at Calc Chat. 127 should be at Calc Chat. The Putnam challenges are, by definition, really, really tough. So if you really find all this way too easy and you want to do a Putnam challenge, knock yourself out, but you're not required. Okay, now this next section, to me, just by the definition, it almost doesn't make a lot of sense, okay? Yeah, I've got to end this and go to 1.5. And there's a reason why they do it, but I'd still find the nomenclature to be less than optimal, I would say. Hopefully it'll let you see why in just a minute. I don't have a lot more time, but let's at least get started. If I can get it to open, I have to keep checking and making sure my computer's still running properly. But I cannot get this to open. Why not? Everything seems to be frozen here. Okay. I just do that to make it release it. No, it's still doing it. Well, let me try that one more time and pay more attention to what it says. Everything's fine there. I hate to do that. But I can't get it to do anything else. So I guess I'm going to have to close this. And it won't even do that. I don't know what they mean by account settings. Does anyone? Okay. All right. Let me try it one more time. Ha! This is it. I guess I confused it enough it gave me what I wanted. Okay. Still recording. Now, here's my problem. That doesn't even make sense to me. Infinite limits. If it has a limit, it can't be infinite, can it? I mean, isn't that a misuse of terms? What they're talking about, what if something doesn't have a limit, not because there's a hole in the graph, but because it's just heading out somewhere, positive or negative. Those are what they're calling infinite limits, which to me are not limits at all. If they were limits, they wouldn't be infinite, right? I don't know. I'm just being picky, I guess. Determine infinite limits, even though that doesn't make, from the left and from the right. Find or sketch the vertical asymptotes. Now that makes sense of the graph of a function, okay? So for the purpose of vertical asymptotes, we're going to do this. But again, to me, this is a stupid use of phraseology, infinite limits, though all calculators use it. It just seems crazy. Consider the function f of x is equal to 3 over x minus 2. Okay? What would be the problem with that? Where would you have a problem? Would you have a problem? Are there no problems at all with it? F of x equals 3 over x minus 2. Yeah, that denominator could be 0, and where would it be 0? At x equal 2. There would be your problem case, okay? Now, if x was approaching 2 from the right-hand side, this would be a positive fraction, right? But if it was approaching 2 from the negative side, that would be a negative fraction, okay? And those fractions would just take off and go in opposite directions, okay? So from this figure, which is exactly what we saw here, x equal 2, approaching from the right, it's getting infinitely large, approaching from the left is going infinitely small, okay? You can see that f of x decreases without bound as x approaches 2 from the left and approaches without bound positive infinity approaches 2 from the right, okay? Increases without bound. Decreases without bound here, increases without bound there. So if it increases or decreases without bound, how can you talk about a limit? I mean, it just seems ridiculous to try to talk about a limit, okay? Now, this is all absolutely correct. As you get closer and closer to from the right, from the left, this is getting closer and closer to from the left, this is going to be incredibly large negative values. You're getting closer and closer to 2 from the right, this is going to incredibly large positive values. So there the twain to meet. I mean, they're getting further and further apart rather than closer and closer together. So it's either increasing or decreasing without bound. So that behavior is denoted by this, okay? Which the limit as x approaches 2 from the minus side of this thing right here, they say is negative infinity, which is not a number, okay? It is, the limit to me should be d in e, does not exist. You know, but it says it's negative infinity, which means it doesn't exist. And from the right, it does not exist, but it's going to infinitely large numbers. The symbols refer to positive infinity and negative, positive infinite and negative infinity. One of these should be in infinity or infinite. I mean, that should be infinity, okay, respectively. These symbols do not represent real numbers. They are convenient symbols used to describe unbounded conditions more concisely. So I guess rather than saying doesn't exist, you can say that. But to me, that's a poor substitution. Okay. A limit in which f of x increase or decrease without bound as x approaches c is called an infinite limit, which then to me is a contradiction in terms. If it's a limit, it's not infinite. If it's infinite, it's not a limit. Definition of infinite limits. Okay, if f is a function that is defined to every real number on some open interval containing c, except possibly at c itself. And that's really important here because the limit as x approaches c doesn't exist. Okay, so it does not exist except at c itself. It means that for every m, capital M, greater than 0, no matter how large you make that m, there is some delta greater than 0 such that for f of x is greater than m, no matter how big you make it, whenever the x minus c is less than delta. You can find some delta that no matter how big you get that m, you're not going, this thing, f of x is going to be greater than m. That means, and then the statement going to negative infinity. Some books use a little m here. This one uses capital N. It doesn't really matter. There is some delta that anywhere past that, no matter how small you make that n to be, you can find for some delta greater than 0, f of x would be even less than that tiny little n that you have there whenever that difference is less than delta. So to define the infinite limit from the left, there is no definition because it doesn't exist, okay? Replace this by that, and to define the infinite limit from the right, replace this expression here with that. There is some value out there that's in between c and c plus delta, and for every x in there, you're going to be beyond what your supposed maximum was. Now here's what it means, okay? This is one example of infinite limits, okay? Here are two values, This is, I'm going to jump ahead and call, that's your vertical asymptote. At x equals c, you cannot ever be that. Ever. That's going to be where your denominator is 0. When you're approaching c from the left, it's going infinitely large. From the right, it's going infinitely large. Never will meet. No matter how far up here you went. And the closer and closer they got together, you could always find an m, a delta greater than that, some positive delta, it could even be greater up there. So, to me it just says the limit doesn't exist. They call it an infinite limit, which it just sounds bad. So determine the limit of each function shown in the figure here. They're not giving us, oh yeah, they're giving us a function. This is the one like we just saw, where x equal 1 obviously is going to be your vertical asymptote. That's where you can't exist. And when you're approaching 1 from the left, x minus 1 is a negative number, but when you square it, it becomes positive, and you're taken off. 1 over a very tiny, small positive number is going to be a huge positive number. And this, when x is greater than 1, of course, x minus 1 is going to be positive, but when you square it, it stays positive. It gets even larger, and so that's going to infinitely large even faster. Okay? Now, this one, without the square down here, when you're approaching, because you have a negative up here, if you're approaching x from the left-hand side, from the minus side, then x is approaching 1 here. This is negative, but that's negative, so the quotient will be positive, infinitely large positive. And down here, because the numerator is negative, but the denominator here is you're approaching from the right-hand side, x is greater than 1. So that is negative, positive, but that's negative. So this is going to negative infinity. But you see, in both cases, I would say they don't exist. Okay, what they say, both of those are going to positive infinity. The left is going positive, the right is going negative. Just another way of saying it, but the limits don't exist. That's, to me. When x approaches 1 from the left or right, the x minus 1 squared is still positive. So that is going to an infinitely large number from either side. Okay? And that's exactly what we saw. But when it's not squared, then as x approaches 1 from the left-hand side, that's a small negative number, so its reciprocal is a very large negative number. The quotient then would be a large negative. Oh, well, but the numerator is also negative, so that makes it a large positive number. Okay, because the numerator is always negative. So that would be going to positive infinity from the left, negative infinity from the right. Except those aren't numbers. Okay, infinitely large, infinitely small. Okay. And again, oh yeah, and that example 2, is that the one we just did? No, that's what we're starting to get at. That was example 1. So let's look at vertical asymptotes. If it were possible to extend the graphs toward positive, negative infinity, well, of course you could, but you just could. You would see each graph becomes arbitrarily close to the vertical line x equal 1. These get closer and closer and closer and closer and closer and closer to negative 1. Here, this one gets closer, that one gets closer, but they never reach, x equal 1, not negative 1. Okay? That line is called the vertical asymptote. X equal 1 is your vertical asymptote. And y'all did this in pre-calculus, I'm sure, right? Okay. So here's the definition of vertical asymptote. If f of x approaches infinity, or negative infinity, any infinity, as x approaches c from the right or from the left, then the line x equals c is a vertical asymptote of the graph. Okay? So in example 1, note that each of the functions is a quotient, and that the vertical asymptote occurs when the number at which the denominator would be 0 and the numerator not 0. Because if both of them are 0, what kind of form do you have? indeterminate. You can't say it then. But if the denominator is 0 and the numerator is not, then you have a non-defined term, and that's the one where you have a vertical asymptote. So this theorem generalizes that. If f and g are both continuous functions on an open interval containing some point c, if f of c is not equal to 0 and g of c is equal to 0, then there exists an open interval containing c such that g of x is not 0 for all x's other than c. X equals, when x is not equal to c. Boy, this is a bunch of double negatives here in the interval. Then the graph of the function h of x, f of x over g of x has a vertical asymptote to c. Now what they're saying here, g is some function that is a variable function. Okay? And it only has one value at which it's 0, and that would be at x equals c. C plus a little bit, c minus a little bit, g is not equal to 0. Then that would be it. Are we running out of time? Yeah, I think we have. So we'll pick up with this next time. We will pick up right there. This is 1.14. Okay, we probably didn't get enough done in this section for any additional homework exercises, so we'll go from there. I will try to have ready for you your first test next time. Okay? It's Wednesday.
I have a question. It's on infinite. No, it's not on infinite.
Yeah, but let me just get this in place.
So I know last section. I believe it's not that, but that.
Yeah.
Can you explain this? I just don't understand.
Okay.
So if you approach it from the left, you have a -1, but if you approach it from the right, you have a 0. I just don't.
Okay. Okay. Do you understand what they mean by the step function, the greatest energy function? I mean, that's what it is. Okay. Maybe this will make more sense to you. Mm-hmm. Think of mailing packages.
Yes, sir.
Okay. Let's say you first have a little letter that you're sending, and it's less than an ounce. It's going to cost you whatever the cost is now. What is it, 54 cents? I don't know what it is. It's going to cost you something. But if you put more in that package and it got between 1 and 2 ounces, then it's cost you more, right? Between 2 and 3 ounces, it's going to cost you more. Between 4 and 5, every ounce you go up.
Yeah.
Okay. That's a step function. It's going to cost the same amount, 0 to 1 ounce. It's going to cost the same amount from 1 to 2 ounces, but it's just going to be more than that. It's not a continuous thing, it's a step thing. Does that make any sense?
Yeah.
So as you're approaching 1 ounce, the limit here is 55 inches, the limit there would be 86 inches.
Okay. Say that again?
Cents, I was saying inches, cents.
Oh, okay.
Yeah. If you're approaching 1 ounce, it's, I don't know what the price is.
Oh, yeah, 55.
55 cents. But if
But
you're
if you're
approaching
over
that and approaching 1 ounce, it's going to be 86 cents. So whatever the next denomination is. Mm-hmm. That's what this is.
Well, can you explain that in terms of this?
Well, you see at each interval here, it's the greatest integer here. So pick a number. Just give me a number.
Right. We'll use 3.
Okay, 3. Greatest integer in 3 is 3. Okay, so that's... Okay, now this is a different one. No, it isn't. Okay.
Is it? Well,
no, they haven't shown the next one. Okay, at 3, that would be up here. That would be right there. Yeah. At 3, it would be up here.
Never mind. Use 2 then. Just use 2. Let's use 2.
2. Okay. At 2, it's 2.
All right.
At 2.1, it's 2. At 2.2, it's 2. At 2.3, it's 2.5. 2.7, it's 2. Anywhere in between 2 and 3 the value is 2. But when you get to 3, it jumps up to 3. It's just like the postage. When it reaches an interval,
then it jumps.
It jumps.
Okay. So
okay. So as x is approaching 2, say, from the left-hand side, the value is always 1 up until it gets to 2, and then anything past that from the right-hand side, the limit is 2. See, the limit down here is 1. As you're approaching from the left-hand side of 2, that value is 1. And as you're approaching from the right-hand side, anything greater than 2, the value is 2. But at 2, it jumps up from 1 to 2.
Okay, so therefore, limit when it's going to 0.
Okay? Going to 0 from the left-hand side, you're down here at -1. From the right-hand side, you're there at 0.
Damn it.
Does that
You're
make
really
sense?
good at this. Yes,
Oh,
thank you.
not really. Don't spread the rumors around like that. Okay. All right. Good deal.
Appreciate you.
See you Wednesday.